Hey everyone, in this video we're going to learn about residuals. The first thing I want you to think about is a scatter plot. Right, so we have an x and y axes and all these data points plotted. The next thing we often were asked to do was either draw in the line of best fit or find the equation of that line with a linear regression. Very rarely did every data point fall on the actual line of best fit. Most of the time, the data was distributed above and below that line. So a residual is the vertical distance between a data point and the line of best fit. Right? So if we take a data point and we find the vertical distance, so the change in the y, from that point to the line of best fit, that's going to be the residual value. If the point's above the line of best fit, it's going to be a positive residual value. And if the point's below the line of best fit, it would be a negative residual value. And just a reminder, we find the equation of the line of best fit using a linear regression with our calculator. Okay, so we can see here we have the residual defined as the actual y value minus the predicted y value. So we get the actual y value from the data, and the predicted y value comes from the linear regression equation. And we find the difference, that gives us our residual value. Now, once we have a few residual values, we can create a residual plot, which is a graph that shows the residual values on the vertical axis and the independent variable on the horizontal axis. Okay, so let's start here. We have a scatter plot with a line of best fit drawn in. So if we want to find the residual value for, let's say, this data point here. Okay, so we're looking for the distance from the point to the line. Okay, so it's actual minus predicted for the y values. So we can estimate that's about 1.6, let's say. Okay, so that distance right there, that's our residual value. So then we can create a point on the residual plot, same x value, so 8 is the x value, and now the residual value is the y, so it's the 0.8, 1.6. And we can see that plotted right there. And right there's that same distance. And let's take a point that's below. So right here. Okay, so now the residual should be negative. Right, so it's about, let's say, negative 0.8. Okay, so on the residual plot, we'd have a point at 4, negative 0.8. So 4, negative 0.8, about, maybe negative 0.7. But there we have the point on the residual plot. Okay, so a residual plot is just another way to represent our data. Okay. So we talked about how to find the residual values. We can see that the x-axis is the same, right? So 1 to 10. And all that's changed is the y-axis. Now, the y values of each of these points is the residual value. One good way to think about a residual plot is to think of the horizontal axis as the line of best fit. So a residual plot is essentially if we took this scatter plot with the line of best fit and we rotated it sideways so that the line of best fit is now the horizontal axis, right? And now we have a different perspective to look at the data. And we can see how far away each data point is from the line of best fit in a little bit more clear of a way than looking at the scatter plot. Right? That's the idea of a residual plot, just to give us a different perspective to look at the data. Horizontal axis represents that line of best fit, and we can see how far away each data point is. So how can we tell if a linear regression was the best fit for the data? Right? One way we looked was the correlation coefficient. That was the previous video. Now, residual plots will give us another way to decide if a linear relationship was exhibited by the data. So if the points in a residual plot are randomly dispersed around the horizontal axes, then a linear regression model is appropriate for the data. If the points in a residual plot show a non-linear pattern, then a linear regression model would not be appropriate for the data. Okay, so we can see a few different residual plots. So this is an example where the points are dispersed randomly around that horizontal axis, right, which we are thinking about as the line of best fit. So a linear function would be a good model for this data, right? The data shows a linear relationship. If our residual plot looks like a U-shaped pattern or something that's a nonlinear pattern, right, then a line would not be the best fit, right? So a nonlinear function would fit this data better. Now I know it's tempting to say, well, maybe it's a parabola. We can't make that conclusion. All we know from this is a linear function, a linear relationship is not apparent. That's all we're doing. Linear or not linear. The table below represents the residual values for a line of best fit. Create a residual plot for the table and use it to determine whether or not the line is a good fit for the data. So they've already done the hard work for us. They've found the residual values. Now our job is just to create the residual plot and use it to determine if a linear function was the best fit for the data. Okay, so x, we have to go up to 9. So we'll just go by 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll stop there. And then for residuals, the highest is 2, the lowest is -2. So let's go every 2 boxes is 1. 1, -2. Right, so these are the residuals. Okay, so now we can plot each point. So the x value stays the same, and now the residual value is the y. So 1, -1, 3.5, 4, 1, 4, -2, 6, 1.5, 7, -0.5, 8, 2, 8, 0, 9, -2. Okay, so looking at this residual plot, there isn't any U-shaped pattern that I see, or a nonlinear pattern. Right? The points are pretty randomly dispersed above and below. And there's a few points above, a few points below, no pattern. So we can say that the residual plot is random. So a linear function is a good fit for the data. Okay? That's our end goal. That's why we're creating these residual plots. We want to be able to decide if a linear function is a good fit or not. Again, we did this with correlation coefficient. This is another way to make that decision. The line of best fit for the following data set is y equals x plus 9. And here is the data set. Create a residual plot for the data, and then does the residual plot indicate that a linear function is a good fit for the data? So in this example, we have to create the residual values, or find the residual values. Okay, so we have our actual, right? These are the actual data points. We need to find the predicted y values. And we're going to do that by using the linear regression. Okay, so when x equals 4, the predicted value would be 13. When x equals 6, the predicted value would be 15. X equals 10, the prediction would be 19. 12, prediction would be 21. 18, we'd have predicted value of 27. And at 20, predicted value would be 29. So now we can find the residual values. So remember, residual is actual minus predicted. And our setup actually works out perfectly because we just have to subtract straight down. So 11 minus 13, that would be -2. 18 minus 15 is 3. 16 minus 19 is -3. 24 minus 21 is 3. 23 minus 27 is -4. And 30 minus 29 is 1. So there we have our residual values. Okay, so x, we have to go all the way up to 20. Okay, so we'll go by 2's. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We'll stop there. And then for the residuals, we have to go up to 3 down to -4. Okay, so we'll just go by 1's. So 1, 2, 3, 4, -1, -2, -3, -4. Right, and these are the residuals. Okay, so we need to plot our residual values. So remember, x value stays the same. So the first point will be 4, -2. So 4, -2. And then 6, 3. 6, 3. 10, -3. 10, -3. 12, 3. 18, -4. 18, -4, and 21. Okay, so there we have our 6 residual points. And now we need to decide if this residual plot indicates that a linear function is a good fit. So again, we're looking to see if there's any nonlinear patterns represented in this residual plot. Well, not that I see. The points are pretty randomly dispersed, right? 3 above, 3 below the horizontal axes. So then I would say that this residual plot is pretty random, which then indicates that a linear function is a good fit. Okay, so we could say it's random. So a linear function is a good fit for the data. Right, so we abbreviated the same sentence we wrote in the last example, right? Just cutting a little bit out, just saying we have a random residual plot, so we know a linear function would be a good fit for the data. Right, and notice here we now are going a little bit further away from the horizontal axes, but it's all relative. Right? Even if we're going by 10s, if that's the scale that we're working at, we're still looking for that random distribution about the horizontal axes. The table below represents the hours 10 children spent at an amusement park and the number of rides they went on. So we see all that data in the table. Create a scatter plot of the data and draw in the line of best fit. So hours need to go up to 6 and the number of rides need to go up to 20. So we can start by scaling our axes. So we'll put hours on the horizontal axes and the number of rides on the vertical. So to space out the hours, we'll go every 2 boxes is 1, 2, 3, 4, 5, 6, 7, 8. We'll stop there. And then we need to go up to 20 on the vertical axis. So we'll go by 1s and we'll label every other. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so now we can plot the data points. So 1, 3, 2, 5. So 1, 3, 2, 5. 2, 8, 3, 4. 2, 8, 3, 4. 3, 6, 4, 10. 3, 6, 4, 10. 5, 10, 5, 14. 5, 10. 5, 14. And then last ones are both 6, so 6, 15. and 620. Okay, so there we have our scatter plot. We want to draw in the line of best fit. We're going to estimate it as best we can. So that looks like a pretty good estimation for the line of best fit. Might not be perfect, but we'll find that equation when we use our calculator. So we have our scatter plot and the line of best fit. Now we want to transition into creating a residual plot. State the linear regression equation for the data where the number of hours spent at the amusement park is the independent variable. Round all values to the nearest tenth. Okay, so I'm going to go to the calculator, stat, edit, hit enter. You'll see I've already put this data set in to save a little bit of time. Okay, so you want to put in L1, you want to put in L2. Pause the video if you need time to do that. Make sure you have the same number of entries in each list. Once you've done that, we're going to hit stat, over to calc, choice 4, down to calculate, hit enter, and I'll drag the screen into our notes and make it a little smaller. Okay, so there we have our linear regression. We're rounding to the nearest tenth, so the linear equation is y equals 2.8x minus 0.7. What is the correlation coefficient? Round to the nearest hundredth. What does this value tell you about the data? So correlation coefficient is r. So rounded to the nearest hundredth, so that's 0.89. So it's positive, so there's a positive correlation. It's close to 1, so there's a strong correlation. So we'll say that there's a strong positive correlation with this data set. Is there a causal relationship? Explain your reasoning. So by spending more time at the amusement park, does that cause you to go on more rides? And the answer there is no, right? There is no cause and effect. You can spend a lot of time in the amusement park and go on no rides, right? So is there a causal relationship? No. Increasing time at the amusement park does not cause you to go on more rides. Perfect. Okay, so this tied in a little of the old stuff with the new stuff that we've been doing. But the important part here is we have that linear regression equation, and we're going to use that to find our residual values. Okay, so create a residual plot. So hours was X, number of rides is Y, right? And this is the actual data points. So we need the predicted first. Hey, one way to do this quickly, if this is our equation, is to go in the calculator, go into y equals, and type in our linear regression equation, which is 2.8x minus 0.7. And we're not going to graph it, but we'd hit second table. And very quickly, we can have the values from 0 to 10. We can scroll if we need more values there. So I'm going to bring this in here. And then I'll delete it once we've written everything out. So at 1, the predicted value is 2.1. At 2, 4.9. 4.9. 3, 7.7. 4, the predicted value is 10.5. 5, 13.3. At 5, 13.3 again. And 6 is 16.1. Okay, so I'll get rid of this, give us a little bit more room. Okay, so now we need to find the residual value. So remember, that's actual minus predicted, so we're going to subtract down. So this would be 0.9, 0.1. Here we'd have 3.1, then negative 3.7, negative 1.7, negative 0.5, negative 3.3, 0.7, negative 1.1, and 3.9. Okay, so there are the residual values. And we have a lot of decimal values here. And we need to create our residual plot. So ours at the amusement park, that will still be the horizontal axes, so 1 through 6. So again, we can space it out here. So we'd have 1, 2, 3, 4, 5, 6. And let's see, 3.9, negative 3.3. So we'll go by ones here. So 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. And these are the residuals. Okay, so now we will plot them. So we have a point at 1, 0.9. So right about there. Then we have the next two are at 2, so 0.1 and 3.1. So 0.1, that's right about there, and then 3.1. Then we have the next two at 3, so negative 3.7 and negative 1.7. So negative 3.7 and negative 1.7. 1 at 4, negative 0.5. That's like right on top of the 4 that we labeled. Then we have 2 at 5, negative 3.3 and 0.7. So negative 3.3 and 0.7. And then we have 2 at 6, negative 1.1 and 3.9. Negative 1.1, 3.9. Hey, so there is our residual plot. And we need to decide if the residual plot indicates that a linear function is a good fit for the data. Explain your reasoning. Well, I don't see any nonlinear pattern exhibited by the residual plot. So that tells me that a linear function is a good fit. The points are randomly distributed above and below the horizontal axes. All right, so random. So a linear function is a good fit for the data. Hey, so this is a great question because we covered a lot, right? We create a scatter plot and a line of best fit. That was from the first video. We created that linear regression equation. Then we found the correlation coefficient. We decided if the relationship was causal. And then we finished the question off by creating a residual plot and going through that whole process of finding the predicted y value, finding the residual value, plotting it, and coming to a conclusion. Our last question, which of the following indicates that there is not a linear relationship between the data? Okay, so choice A and B are correlation coefficients. Both of those are strong correlation coefficients, or indicate that there's a strong linear relationship between the data. C, there's a nonlinear pattern, right? There's that U-shaped pattern. And D, the points are randomly dispersed in that residual plot. So looking back at choice C, which is a residual plot with a nonlinear pattern, that would indicate that a linear function is not a good fit for the data. Okay, so that would indicate that there's not a linear relationship. So that covers our residuals. Key idea is that the residual value is the actual value, actual y value, minus the predicted y value. And we get that prediction by using the linear regression equation. Create our residual plot. If we have a random pattern of the residuals, that indicates that a linear function is a good fit. If there's a nonlinear pattern, then it indicates that a linear relationship is not exhibited by the data. Right? A linear function is not a good fit. So now practice a few of these, going through that whole process of finding the predicted value, finding the residual, and creating the residual plot, and coming to the correct conclusion on your own. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.